Hi there. So this is your last lesson of math theory. We're going to do 2 days of material here on 14.4, and then you're going to get your regular work time on Wednesday and Thursday. Please check the calendar in your email. You are going to have an end of year test. It's not going to be a giant, huge final. You will have the chance to correct just like you would on any other exam. But I'm going to give you the next week after this, so May 17th through 21st, to prepare, give you a chance to ask any questions, submit corrections. I would love to chat with you both about anything you're stuck on. There in your email, within the next few days, will be a study guide with a discussion of exactly what the test will look like. And then the test itself will all go live on the week of May 24th through May 28th. There'll be 4 pretty short sections. You can take them at your own pace. You can jump around. They'll be labeled. The recommended due dates are going to be do 1 section each day, Monday, Tuesday, Thursday, Friday, with Wednesday off, but you're able to set your own schedule. Then the last 3 days of school, so June 1st, 2nd, and 3rd, will be a chance to complete any corrections that you want on those short exams, as well as anything from the whole of the course. So let's get started with our last set of notes for this class, talking about what's called the Cantor-Bernstein or Cantor-Bernstein-Schroder Theorem. Now, what this means is about when it comes to cardinalities of sets. So if you probably recall, just in how numbers work, is that if A is less than or equal to B and B is less than or equal to A, then the 2 numbers have to be equal. This, it turns out, is also true with sets. So that if the cardinality of A is less than or equal to cardinality of B, and the cardinality of B is less than or equal to the cardinality of A, then the cardinality of A and B are equal. If you remember from previous lessons, so showing that cardinality is less than or equal to just requires an injection between A and B and an injection from B to A. So if you can do those 2 things, then you have shown that A, the cardinality of A, is equal to B. And it's often a lot easier to write 2 injections versus trying to write 1 bijection. So here's just another tool to prove that the cardinality of 2 sets are equal. So here in number 1, show that the cardinality of 0 to 1 with a closed boundary at 0 is the same cardinality as 0 to 1 with an open bound at 0. So our goal here, I'm going to use the Cantor-Bernstein-Schroder theorem, is to write 2 injections. And often what you'll find with the work for this problem set is that one direction is just a lot easier than the other. So the first one I'm going to write from actually the closed interval, the open interval to the closed. And I'm just going to say that f of x is equal to x. Right? It excludes 0, so it's not a surjection, but it is very clearly an injection. Right? By definition, f of x equals f of y implies x equals y by the definition. Again, it's not surjective because we're missing that 0 here in the codomain, since 0 isn't in the domain, but it's an injection. Now, the other one, so what we've done now is show that open 0, 1 is less than or equal to closed 0, open 1. So now I'm going to try to write an injection from closed 0, 1 to open 0, 1. So we want to be able to write an injection. And the way I think my way through this problem is to say, all right, I want to have 0 as an x value, but I don't want it to end up with 0. And then I want my maximum for both to be 1. So if I want to be able to put in any number, and I just don't want it to exceed 1, but I want it to start, I want to be able to plug in 0. So I'm going to say, there's a lot of options actually here. The one that I used is I said, I'm going to say this is 1/2 x. So that's going to keep it from getting too big. But I want to be able to start at 0 and get a non-zero number, so I'm just going to add a 4th. You could have added a 10th. You could have added something. The idea here is that if I graph out my function, right, this would be the graph of the function. Since I'm only going from 0 here to 1, then the maximum function here would be 1, and all of that is within the range of this function. Again, it's not a surjection. You're missing all of these y terms here. You're missing y terms here, but it is an injection. So you want to make sure that we're not missing any of the numbers in here, but we can see that we go from 0 to 1 just fine, and we're in that set where we're starting at 1/2 and we're maxing out at we're starting at 1/4, we're maxing out at 1/4 plus 1/2. So all of these y values are between 0.25 and 0.75, which is well within this interval. So again, not a surjection, absolutely an injection, which we can prove by saying f of x is equal to f of y. And that implies that 1/2 x plus 1/4 is equal to 1/2 y plus 1/4. Subtract 1/4 on both sides and multiply by 2, and you get that x is equal to y. Now, since we are able to write these two injections, so we can say since the first injection, which says that the cardinality of open 0, 1 is less than or equal to closed 0, 1, and the cardinality of closed 0, 1 is less than or equal to the cardinality of open 0, 1, then we can conclude that they are equal. That's the use of the Cantor-Bernstein-Schroder theorem. Now, several of your homework assignments are going to deal with power sets. So here it wants to show, and this is one of the most crucial ideas in the study of infinity, is show that the power set of the natural numbers has equal cardinality as the real numbers. So I'm going to use a trick that I've used a lot of times here, which is the idea of I don't maybe want to write injections and bijections with R or with some of these sets. I'm going to remember that, oh, I've already shown that the cardinality of R is equal to some other set. We know this. You know, in number 1, we showed that this is true. So sometimes I can ask myself, okay, well, instead of writing a injection between the real numbers, maybe I want to use one of these other subsets. So I actually am going to use this last one, and so I'm going to show that the power set of the natural numbers has the same cardinality as the interval from 0 to 1. And so I want to write two injections that show that. So my first one, I'm going to say, I'm going to go from the interval 0 to 1 to the power set of the natural numbers. And the way that I'm going to do that is I'm going to think about, all right, well, the elements here, so if I take my x value is somewhere in 0 to 1, so it'd be 0, and there's going to be just a bunch of digits. So I'm going to call that digit 1, digit 2, digit 3, digit 4, digit 5, so on. And I'm going to say that that's going to equal a power set of the natural numbers. The first element in that power set would be 1. Now I won't just say A1, A2, A3 for every digit of the decimal, because then it would have a lot of overlap, because then 1, 2, 1, 2, 1, 2 would point to the same subset as 2, 1, 2, 1, 2, 1, which is not what we want. Then it's not injective. So I'm going to say that the next one is 10, so because the 10th place, times A2, 100, A3, and so on, so that I'm getting a different one, keeping that the order is important. So the idea, so we can show that this is injective because as long as this number is unique, it will have exactly the same elements here. Now to write an injection from the power set of n to the interval 0, 1, right, we are going to take a similar stance where f now, though, is a subset of the natural numbers. So x is a subset of the natural numbers. It's an element of the power set. And we are going to say, it's going to equal a number between 0 and 1. I'm still going to write out its digits in this form. Where a sub I is equal to 0 if I is not in x and a sub I, not in x, is equal to 1 if a is in x. So we're making just a binary shape. So if I have, again, this is not going to be surjective because the only digits in these numbers are 0 and 1. But if I have the subset 1, 2, 4, and 8, it would be 1, 1, 0, 1, 0, 0, 0, 1, 0 for the rest. So it's still going to be unique because every subset is going to have exactly the same digits. So these are both of these are injections. So therefore, hence, injections exist from the power set of n to the interval 0, 1, and back again. So we know that the cardinality of the power set of n is equal to the cardinality of the interval 0, 1. And then therefore, by the transitive property, the cardinality of the power set of n is equal to the cardinality of the real numbers. So I'll often use these tools where I'm going to just use a different fact earlier to figure that out. So the one thing that this is really important is it introduces something called the continuum hypothesis, where n is sort of, we think about it as aleph naught. It's the smallest infinity. And now we know that its power set is equal to the next size of infinity that we can imagine. Now the question is, would this pattern keep going? If I took the power set of the reals, would I get another size of infinity? If I took the power set of that, would it keep going? Is this the way that we can keep sizing up infinity? We don't have the answer to that, that I am aware of at least. So this is one of the next big questions in the idea of set theory and cardinality. And it's one of the things that active mathematicians are studying currently right now. I hope that you've really enjoyed math theory. I've really enjoyed working with both of you this year. Again, be on the lookout in your email for information about the end of the year test. But for the next few days, you can just focus on your last problem sets from 14.4. I'll be available on Zoom by email or in the